Yes, well, thank you very much for coming twice to this seminar. And it is a pleasure for us to have Carlos Bravo Prieto from Freie University of Berlin. Do we say it like that? At ISELTS Group. Thank you. Thanks a lot. The idea of these seminars is that we can have a space to bring people that are super smart, ask a couple of questions and discuss a bit. So it's quite informal in that sense. So if you don't mind that we jump in and interrupt you and
Sure,
discuss
sure.
stuff, cool. So
I
then,
actually prefer that, yes.
that's amazing. So the floor then is totally yours, and really thanks a lot, Carlos.
Yeah, yeah. Thank you very much for the invitation. Hopefully this time we have no issues. So today the idea is to present a work that we published recently and in Nature Communications titled Understanding QML Also Requires Rethinking Generalization. By the way, can you see my pointer?
Sí.
Yeah, yes, okay.
Yes, yes, indeed.
Okay. And as you can imagine, this work was not done in isolation, but it was a nice collaboration with Lia Gilles Fuster, PhD student in the group, and Jen Sizer, who is the PI. So this is the outline of the talk. First, I will briefly introduce some concepts, and actually the main point would be to set the common grounds for what's the context of this work in the whole literature. Then I will jump into something I've called the pitch. Here I will define the problem, and then I will provide the result in just a few words, like in a take-home message style. Then for those who are like really interested in the details, I will talk about uniform generalization bounds and how with randomization tests, we can prove that these bounds might be loose in practice. And then I will just mention a few words about memorization of quantum neural networks, and finally the conclusions and the outlook. So let's start with the introduction. So there are many things that can be rightfully called quantum machine learning. So let me be specific. We, of course, consider three components: model, data, and the training algorithm. For us, the model is going to be quantum, namely parameterized quantum circuits. The data is going to be quantum as well, so we are going to consider quantum states as training data. And then finally, we are going to consider a classical training algorithm like gradient descent, for instance. So what's the motivation of this work, right? So probably you've seen in many introductions in different works saying that parameterized quantum circuits are quite promising for the near term, right? But in the end, the end goal would be to use these parameterized quantum circuits to solve real world problems, like, for instance, protein folding. Now, if we ask ourselves how we researchers study these parameterized quantum circuits, we study them in a, say, holistic manner, right? We specifically study three different branches: expressivity, trainability, and generalization. Expressivity is related to what kind of functions we can say reach with our parameterized quantum circuit. Then trainability is related to what can we reach a good local minima, say training the algorithm with a gradient descent. And then finally generalization, which is related to how well our model will perform on unseen data after the training. So as we said, we studied these three different branches, but this is perhaps a personal opinion, but I believe that generalization is like the holy grail in machine learning and also quantum machine learning. Because in the end, we always train our model with limited data, and we ask ourselves what's going to be the performance of this model on new data. And a clear visceral example of this on why generalization is so important, and I'm pretty sure you know this, but a clear example would be self-driving cars, right? Because in the end, you train this car in a, say, safe environment or in simulation, or I don't know how you do this. You will know better. But at some point, you want to deploy this car into the streets of Barcelona or San Francisco, and you don't want this car to run over people, right? Because otherwise you might be in trouble. So this is a clear example on why generalization is so important. So let me give you a bit of historical context. So starting from the 70s up to until very recently, actually, machine learning practitioners developed some theory, which is called traditional statistical learning theory, which was actually initially developed by Babnik and others. And this theory was used for the models at that time, like small neural networks, kernel methods, and so on, to provide some theoretical guarantees on how these models will perform, namely generalization bounds. Now, it turns out that very recently, a team at Google DeepMind, particularly in 2016, they put on archive like a very nice paper, and the conclusions of this paper were very clear. They said traditional learning theory cannot explain the success of deep learning, and they were very clear about this. So we have traditional learning theory on one hand, and this theory cannot express the known success of deep learning that we experience in practice. So since then, researchers have developed modern approaches to generalization in classical machine learning. I will discuss about this later. Now, if we go to the quantum machine learning field, we see that theory for quantum machine learning started more or less in the 2020s, or actually in the 2020 in particular, where the researchers used this traditional learning theory to develop some new machinery for quantum machine learning models. So in our work, we try to like close this circle, and we are going to show that traditional learning theory cannot explain either the performance of current quantum machine learning models. Okay. So we said that there's no successful quantum
Carlos,
machine
sorry.
learning. Yeah.
One
Yeah.
question.
Mhm.
When you say traditional learning theory, you mean like to quantum traditional learning theory, like from the 20s, or the one from the 70s of Chapkins?
Yeah, but the one from the 70s. So
Okay, okay.
so in 2020, people started using this theory from the 70s that was used
Mhm.
in classical machine learning also until very recently to develop new theory for quantum machine learning models. And that was the precisely perhaps the point I want to make in this slide, which is okay. We said that generalization is important. We've seen how people studied generalization in quantum machine learning models, but we are in a clear elephant in the room situation, right? Because on the one hand, researchers in quantum machine learning knew and were aware about these results on classical machine learning, saying that traditional learning theory cannot explain the success of deep neural networks. But somehow we told ourselves that perhaps for QML models, especially these small QML models, this traditional learning theory could actually explain the performance. And as we will see, this is not the case.
Mhm.
So we've been talking about PQCs, but how do these PQCs generalize in practice? So there's this nice work published in Nature Communications by Matías Caro and some people at Los Alamos. I'm pretty sure you are aware of this work. And in this work, they develop some generalization bounds, which are quite nice, but most importantly for us, they also perform some numerics, and they show that PQCs can actually generalize pretty good, even if you consider just a few training data, right? So this is what it's actually important for us. So we observed that, thanks to this paper, that PQCs can generalize properly. But now our question was, okay, but where does the theory fit into all of this, right? So let me jump into the pitch. So let me start by defining the problem. This is like textbook knowledge, and I'm pretty sure you all know about this, but just to be sure that we are all in the same page. So the task, um, the task will be to, for instance, solve a classification problem, right? So we are given a data distribution D that contains some samples X and some labels Y. This could be samples, for instance, could be photos of cats and dogs, and the labels cats and dogs, right? And this data distribution is unknown but fixed. What do I mean by this? Imagine that, for instance, this data distribution is me taking pictures of cats and dogs. So this is fixed, right? Because it's me, but it's unknown in the sense that you wouldn't be able to mathematically describe uh, myself taking pictures of cats and dogs. This is what I mean by unknown by fixed. So on the other hand, we also have the model, which is a function family that will be parameterized by certain parameters that we are going to fine tune, and that maps these samples to some labels. And finally, ideally, we would also love to assess the performance of this model. And this is done by something called population risk, which takes as input the samples and the labels of the model. And if this population risk is small, then this means that the model is performing nicely on the whole distribution. Now, however, we don't want we actually want the population risk, but the actual distribution D is unknown, right? We said that the distribution D is unknown, although we have access to it. So instead, what we have is a training set. So we have a limited amount of samples. Then we have a performance proxy. So instead of actually computing the population risk, that we cannot because we don't have access to the full distribution, we instead compute the empirical risk, which is similar, but only on the training set that we have. And again, if this is small, this is in general good, right? So in the end, what we have is an approximation of the empirical risk minimizer. So the function that we obtain is going to be ideally the function that minimizes this empirical risk, which is not the same as the population risk minimizer, which is the function that actually minimizes the population risk. So now the question, of course, is, but what about the true performance on the whole distribution? Because we only have access to the performance on the training set. And this is quantized by something called generalization gap, which is the difference between the population risk and the empirical risk. So let me review this, but in a, say, in a picture for those who are more visual. So we have our data distribution D with samples and labels, then a training set of size N. We feed this into our learning algorithm, which is gonna search for a hypothesis within our hypothesis class. Ideally, the output of this algorithm is going to be the function minimizes the empirical risk. And hopefully this empirical risk will be small. But now what we are interested in is in the population risk. So we try to quantify this by something called the generalization gap, which is going to be the difference between those two values. Now, how do we quantify this generalization gap in practice? So here is where theory people start using all the machinery that they have, and they try to prove mathematically a difference on these two values. So this is what it's called the generalization bound, which is a guarantee on the magnitude of this generalization gap. So in the end, you have this difference, which is the generalization gap. But what can you prove mathematically is an upper bound of this generalization gap, which is the generalization bound. So I hope this is all clear. Now, of course, this generalization bound could in principle depend on many, many things, right? It could depend on the structural properties of the model family. It could depend on the shape of the loss landscape. It could depend on the optimization algorithm that you use, whether it's gradient descent or gradient free descent, properties of the data distribution itself. And of course, it could also depend on the number of training samples. And you will have to believe me, but this is a very difficult task, right? So researchers instead always study like restricted cases where they only consider some of these properties. So now let me explain the results of this work in just a few words. So this is like probably the most important slide, like the take-home message. So on the one hand, we have the experimental fact. PQCs have reported a small generalization gap, right? We know this. There are several works, in particular this work by Matías Caro and people at Los Alamos that show this. Then on the other hand, we have a theoretical fact. There are several generalization bounds for parameterized quantum circuits out there in the literature. So the question that we try to solve, say, is this one. Can theory explain the good generalization behavior of parameterized quantum circuits? And the answer is going to be no, as we will see later. So what do I mean precisely by that this theory cannot explain the generalization behavior of Piggy system. So to be a bit more particular, in QML theory, the bounds that were derived are something called uniform generalization bounds. Then in QML experiments, we observe, like empirically, that this generalization gap is small. Okay. What we are going to show in this work is that for the cases where this generalization gap is small, every uniform generalization bound is going to be loose. So on the one hand, from the experiments, we observe that this generalization gap is small, but we are going to show that this uniform bound is too large. Therefore, there's like a big gap in between what actually happens and what the bound says. So it will not provide information on how actually this parameterized quantum circuit generalize. Is this understood? Hopefully, yes.
I think so. Yes. Yes.
Okay. Okay. So let's be a bit more concrete on what are these uniform generalization bounds. So as we said, generalization bounds could depend on many, many different things, right? As we see here on the left. But now what we are going to do is we are going to remove many of these dependencies, and we are going to consider structural properties of the model family and the number of training samples. This is what a uniform generalization bound is. You get rid of everything except these two properties. So as you can see, this is already because if you get rid of so many dependencies, then in the end you can expect that the bound is going to be loose, but you actually have to prove this. So as we said, they will depend on two properties, the number of training samples and the structural properties of the model family. And typically, the dependency on these structural properties is going to be something called a complexity measure. Like for example, the VC dimension. I will provide an example in the following slide. And perhaps you are familiar with these kind of things, VC dimensions, Rademacher complexities, pseudo dimensions, and these kind of things. And some examples that you can see in the literature, these are some of them, where they derive uniform generalization bounds. These complexity measures may depend on several things, for instance, the number of gates, the size of the Fourier spectrum, the number of trainable parameter gates, and also in some cases the amount of magic. So as you can see, this is not something like accidental. It's not like there's a single work in the QML literature deriving uniform bounds. This was like the state of the art, trying to derive this kind of bounds to understand generalization in QML. So as an example of a complexity measure, so that it's a bit clearer to you, the VC dimension is an example. The VC dimension is the maximum number of data points that can be shattered by a model. So namely, independently on how many training points I give to you, if and how I label them, you should be able to, the model should be able to fit those points. So an example for 3 points, for instance, if I randomly label them and a linear model, for instance, could fit them, this means that the linear model can shatter 3 points and that the BC dimension of this model is 3. Now, if we consider still a linear model, but we consider 4 points, for instance, there's a case where the model cannot fit the training points, and this means that, of course, the BC dimension is 3. Right? So this could be a complexity measure used to derive non-uniform bounds. So let me give you the explicit template for this theorem. So if you go to any of those papers in the literature, you will see something like this or similar. Let X and Y be the data space. Let F be the hypothesis family. Let R be the population risk, and let C of F be the complexity measure. Let D be any data distribution. This is important. So the theorem applies to any possible data distribution. And let B S any training set of size n sampled from this distribution. And let R hat be the empirical risk. Then the generalization bound holds for any function of this function family, and it has a it's similar to something like this. So what's important here is that these theorems apply to any data distribution and to any function family of the model. And the dependency is going to be, in general, polynomial with the complexity measure and will depend inversely on the number of training samples. So keep in mind that the important thing here is that these apply to any data distribution and to any function of the function family.
This
This is
square
actually
root
what.
is like some sort of central limit theorem, or
Say it again. I can hear you.
the square root of n is like central limit theorem, or
Uh, to be honest, I'm not sure.
okay. And this
Um,
is super general, like
this is
classical.
yeah yeah this is quite general. I haven't seen like any of those theorems where the square root of n is not there. Honestly, I'm not sure why this appears there.
Okay,
Yeah, I've never derived a uniform bound, so I'm not sure. Yeah. So as I said, this is uniform because it holds for any hypothesis F and for any data distribution D. Now, why people derive this kind of bounds, right? And I would say there are like three main reasons. The first one is that they can be used to certificate whether the hypothesis that you get performs well on new data. Then probably the most important part is that they can be used for inspiration to design new models that perform better, right? So if you know how the generation depends on properties of the model, then you can somehow align these properties of the model to perform better on new data. And then, of course, as for us scientists, it's also important to have a more complete understanding of generalization, which is also great. So now imagine I'm going to try to show you how we can prove that these uniform bounds are loose. Okay, or this is like the sketch. Imagine that you are given a data distribution d hat for which learning is impossible. Okay, so you cannot learn this distribution d hat. This means that the population risk is going to be always large for any f, for any function in your hypothesis family, right? Because distribution learning is impossible of the distribution. So by definition, this population risk is going to be large. And now imagine that we draw, say, a corrupt training set from this distribution. If we find a function within the model family that is able to fit this training set, then the empirical risk is going to be small, and therefore the generation gap, which is the difference between the empirical risk and the population risk, is going to be large. Okay, you agree with me with this? So by construction, if we manage to find a distribution D hat for which learning is impossible, independently of on what neural network we use and how large is it, it's always this population risk is going to be large. However, for a finite training set, it may turn out that the network manages to fit the data, even if the data is corrupt, and therefore we are going to have a large generation gap.
It is
Hopefully
a bit
this.
like simplifying, no? Or like taking an easy subset.
No. I mean, the model, for instance, if the model is too large, the model could memorize the training points, could overfit, right?
Mm-hmm.
So if
Mm,
we
okay.
if we reach this, so learning of the whole distribution is impossible, but it may happen that the model could overfit a small, say, training set, even if learning is impossible. So the model would have not learned anything. It would have simply overfit the training data. So you reach this scenario, this would necessarily mean that generation gap is large, right? Because this would be large by construction, and this would be small, right? So the simplified message of this is that if a hypothesis class can fit a corrupt training set, then uniform generation bounds are large for that class. You see? Because the bound is going to be always larger than the generation gap. And if the generation gap is large, the bound is going to be larger. Is this understood? So the goal is going to be to construct a corrupt distribution for which learning is impossible, and then hopefully manage to fit a training set sampled from this distribution. So how are we going to do this? This is done by something called randomization tests. So a well-posed machine learning problem could be, for instance, to take the CIFAR10 dataset and try to classify images of cats and dogs, right? This is something we could do with our neural network. Now what we could do is to partially corrupt the labels. So with certain probability, we could randomize the label of this picture, and therefore some of them are going to be correctly labeled, and some of them won't be correctly labeled. And we could ask the neural network to try to fit this training set. But we could even go further on this, and we could completely randomize the labels. Right? So most of them are going to be incorrectly labeled, and some of them by chance are going to be properly labeled. So here, for instance, this would be a case where we would have a distribution for which learning is impossible because the labels are completely random. So there's nothing to learn here. We could also, instead of randomizing the labels, we could, for instance, randomize the inputs. So we could label random Gaussian noise and try to classify these images. So with this picture in mind, this is actually what we did, but instead of using images of cats and dogs, we used quantum data, right? So if we manage to, I think I will explain this, but if we manage to fit this corrupt distribution of quantum data with random labels, then we are going to show that uniform bounds are loose for that particular class of quantum neural networks. So this is like the.
I am a bit lost. Sorry.
Okay.
What you are saying is that so you motivated this saying that the uniform generalization bound is loose and it's not useful to explain the theory that tells us that parameterized quantum circuits can actually generalize well.
Yeah, this is what we are gonna where we prove in this work.
Okay. Okay. So in principle, even in this scenario of random labels, there should exist some sort of theory that explains that parameterized quantum circuits can actually learn in this scenario. Because there is nothing to learn,
no, exactly. There's nothing to learn. That's why. So I think I understand what you say, and but it should. So the bound. I think I kind of get. What
Sorry,
you say.
maybe it's too much of interrupting. And
No, but it's not that the bound has to explain the theory for this particular scenario. Is that if you show that the bound that the model say fits this training set, which is corrupt, while at the same model could fit original and real labels, then it means that the uniform bound cannot explain the success of the model on real labels because it's gonna be. But this is like the whole point. This is what I'm gonna explain this figure. This is like the whole framework.
got it.
Let's see if it's clearer after this slide. So we are going to implement this randomization test to see whether quantum models can fit random data and how this explains why uniform bounds are loose. So let's imagine that we have the original data distribution D. We have some quantum states with some labels. We feed this training set into a quantum neural network. We train this quantum neural network. We get some F original, some output function. And let's say that it manages to fit the training data well, so the training error is small. And let's imagine that it also performs well on test data, so the test error is small. Therefore, the generation gap, which is the difference between these two values, is going to be small, right? So this is what we observe in experiments, for instance. And this is what we observed on for instance, Matthias Caro paper with Los Alamos people. Now, let's consider a randomized data distribution, D hat, where we randomized the labels. So we consider the same quantum states, but now the labels are completely random. We fit these quantum states with the labels into a into a quantum neural network. We train this quantum neural network, and let's imagine that we manage to obtain a function within this model family that fits the training data. Okay, as we discussed, this is possible in principle. You could overfit the data, and that's it. It's not that you've learned anything because there's nothing to learn. You simply manage to fit the data. Therefore, the training error is going to be small. However, if you now observe what happened with the test set, of course, the test set is going to be, the test error is going to be large, right? Because you cannot learn this distribution with random labels. So the test error is going to be large, like by construction. This means that generation gap, which is the difference between these two values, it's going to be large, right? So we have on the original experiment, the generation gap is small, and in this contrived example, the generation gap is large. Now we go to the QML literature and we look at these uniform generation bounds. These uniform generation bounds say that for any function in the hypothesis class and for any data distribution, the generation gap is going to be smaller than some particular value that provides the bound. Since we observe and we managed to get an example from which the generation gap is large, this necessarily means that the bound is going to be larger than this value here. Therefore, it cannot explain the real scenario where we had a small generation gap. Is this understood, Matthias? This is like the whole point. So if we manage to get a scenario for which we get a function that fits random data, and therefore we force the generation gap to be large, then this would mean that the bound is necessarily larger than this large value, and therefore cannot explain this small generation gap on the real data. Because uniform bounds apply to any function of the family and to any data distribution. So we are within the setup considered by these uniform generation bounds. So we try to trick somehow the system. You know, we go to extreme case, but still within the template of uniform bounds, where we can use any distribution because this is allowed by the bound, and we are allowed to use any function within the function family. So we go to the extreme case where we randomize the labels, where we know that learning is impossible. And if we manage to get an explicit empirical example where we get a large generation gap, then this means that for the cases where this generation gap is small, you cannot explain them by looking at the uniform bound, because this uniform bound is necessarily loose and provides no information.
I have a question.
Yes.
So as you said, for the uniform generalization thing, you are overlooking many factors, right? So which does
Yes.
not allow you to. So by this randomization, which
Mhm.
factor do you impose on this bound? Like, so because of course it cannot explain this original thing
Mhm.
once you have this randomization, right?
It
Uh,
it actually can. So
uh,
so this, I think this is something. Yes, I'm gonna explain the next slide precisely, but we are gonna show that. Okay, let me jump to the next slide and then
okay,
perhaps
okay.
I try to answer your question. But okay, so this is more or less clear. Then let me repeat the simplified message, which is if hypothesis class can fit corrupt training sets, then this means the uniform generation bounds are large for that class. Okay, this is like the conclusion that we've reached. Now, there's a small disclaimer, which I think it's related to your question, which is that these randomization tests cannot succeed for arbitrarily large training sets, right? Because at some point, if I keep growing the training set, the size of the training set, the quantum neural network or the neural network won't be able to fit like the whole a corrupt training set distribution, right? Because it's going to be too large, and then the network won't be able to overfit the data, and therefore the training error is going to be stop. It's going to stop being small. It's going to be large, and therefore eventually the generation gap, which is the difference between the empirical risk and the population risk, which are going to be both very large, will result in a small thing. So this is just to say that we are not proving that these bounds are mathematically incorrect. They are correct in the limit of large training samples. I think this is related to your question. So they are mathematically correct. Simply the case that if you consider a finite, training set size, then it may happen that you fit corrupt data. And in those scenarios, the uniform bound is going to be loose.
Okay.
But if you go to the limit of a large amount of data, then of course the network won't be able to fit all the corrupt training set, and then the bound will predict properly what happens with the generation error.
Okay. Okay.
Yeah. Okay. So math must prevail. So now let me mention the type of experiments that we implement. In particular, we reproduced the experiments on Matthias' paper. The learning task is going to be a classification of ground states of the generalized cluster Hamiltonian, which is this one here, which has different many-body operators, C, XX, and so on. But these ground states can be classified in 4 different phases, which are here. So we are going to sample ground states from this region, and we are going to try to classify these ground states. Now, the point, of course, is that we are going to also randomize the labels and see what happens. The quantum model that we are going to use is the quantum convolutional neural network. Probably you are aware of this, already know this model. This model was inspired by classical convolutional neural networks, where you try to reduce the dimensionality and so on by applying some convolutional and pooling layers. So you try to do something similar, say, with quantum circuits. You apply certain two-body gates with parameter sharing, then which are the convolutional layers. Then you apply the pooling layer, where you measure some of the qubits, and you repeat this to reduce the dimensionality. And yeah, this model has some nice properties, like they can exploit local correlations, and it was also shown that there are no Barron plateaus in these models. So what we are going to do, we are going to corrupt this distribution and train. And again, if the training error is small on this corrupt distribution, then it means that uniform generation bounds are large for that quantum model and in that scenario. We're going to do this for real data, random labels, and then we are also going to randomize the quantum states and see what happens. And then we are also going to perform some numerics with partially corrupted labels. So these are the first numerical experiments. Here, what you see here, it's an average of simulations for different number of qubits, 8, 16, and 32 qubits. What we are plotting is the generation gap as a function of the training set size. So first, if we look at the blue, for instance, which are the experiments for completely random labels, we see that for small training set sizes, the generation gap it's maximal. So it's 0.75, which means that since we have 4 classes, it means that of course, the neural network, the quantum neural network is random guessing. But at the same time, since this is the difference of the empirical risk and the population risk, if we observe here a 0.75, it means that the training data it's completely fit, right? So the population risk is going to be always 0.75, and the difference between this population risk and the empirical risk is the generation gap, which is what we plot here, and it's still 0.75. So this means that we managed to fit all the corrupt training set up until 10 training points. Now we keep increasing the size of the training set. Of course, this generation gap decreases, as we said earlier, where we mentioned that math must prevail. We keep increasing the size, then the model is not able to fit all the training data, and then the generation gap eventually reaches something close to zero. Now, if we look at what happens with random states, we observe something very similar. We manage, so here the random guessing is 0.6 more or less, because if we look at the figure, some of the classes are smaller than others. That's why we don't have this 0.75, but here random guessing, it's a bit biased, and the actual value is 0.6. But again, for small training set sizes, we manage to fit this corrupt training set, and as we increase the size of the training set, then it again decreases. And then for real data, we observe that as we increase the number of training points, the performance is better. And of course, there's a huge gap between both scenarios, right? So this would mean that uniform bounds are quite loose in explaining what actually happens in the real experiment. So the main message here is that quantum convolutional neural networks can indeed fit random distributions. Now, we also did some other experiments with partially corrupted training data. The experiments are run with 8 qubits. Here we can see is the test error as a function of the label corruption. So 0 would mean that there's no corruption, and 1 would mean that we have fully random labels, as in the previous case. And we used different training set sizes. And as you can see, you observe the same behavior independently of the size of the training set. With no label corruption, you have small training errors, and as you increase the randomization, then you in the end reach the random guessing. But this is done like slowly. There's a clear interpolation between this scenario and this scenario, and you can fit the training data in all cases. But still, here, for instance, we don't observe like the random guessing, because the quantum convolutional neural network manages like to extract some signal, even if some of the data is corrupted. That's why we don't observe the random guessing. And then we also plot here the training error as a function of the training time for different label corruption. And we actually observe is that independently of the corruption of the labels, the optimization time seems to be unaffected, which is something interesting, and that was also observed in the classical paper by Google DeepMind. So the main message of this figure is that quantum convolutional neural networks can indeed memorize noise and also fit the remaining signal. That's why we see this interpolation. So simplified message again, hopefully this is the last time I put it here, but this is like the main take-home message. If a hypothesis class can fit a corrupt training set, then it means that uniform generation bounds are large for that class. So what we found empirically is that QML models can fit random labels, quantum states, fit labels to random quantum states, and also fit partially corrupt labels to quantum states. So the conclusion of these numerics is that all uniform generation bounds are large for that class of existing QML models, in particular quantum convolutional neural networks. Okay, so hopefully, are the experiments clear? So what we did was...
Yes, I have a question. Would this make sense in a generative model framework? When you don't have labels, but you can measure against the test set, for instance.
That's a good question. I think this is something we consider as well. It could be, it's all about looking at the literature and whether there are uniform bounds for generative models, which I'm not sure. Classical literature probably. For QML, I'm not sure. And then how would you construct the randomization test? If that's the case, I don't know about that. Do you have any idea? How would you do it for generative models?
No, I don't know, but I guess you could construct it wouldn't make much sense, but you could construct a different kind of data against the test set, but then I don't know if the same rules kind of apply.
Yeah, I'm
I
not
guess
sure.
you need to randomize the like in unsupervised learning. You want to somehow clusterize, no? And then you will need to work at that level, maybe. But
Yes, but it was so okay. Um, would you say unsupervised learning is the same thing as generative modeling? I was
no, but I
Depends on
would
the
put it
approach.
inside, no?
say it again, sorry.
I would put it in that box, in that generative
Yes.
models subset of unsupervised.
Yeah. For unsupervised, I think it's a bit clearer to me, but there you would still have, you could still, okay. Yeah, I don't know, but I guess this might be an interesting question to answer if there are uniform bounds in the QML literature for say unsupervised learning or generative modeling. Because if there are no uniform bounds, then yeah, I guess this wouldn't be that relevant, I suspect. But yeah, might be worth thinking about it. I remember thinking about this in the past, and we said, yeah, it's not as trivial as for the supervised case. So let's keep
Okay,
it.
thank you. Thank you.
Yeah. Okay, so just a few words on memorization, but I don't think this is super relevant, but I want to mention something. So last time I put this simplified message. If hypothesis class can fit a corrupt training set, then it means that uniform generation bounds are large for that class and therefore are loose. Now there's a simple follow-up to this message, which is if hypothesis class can fit any labeled set, then in particular it would be able to also fit a corrupt training set, right? This is what we call memorization, which is the ability to fit any possible labeled set. But now in machine learning, we actually don't care that much about memorization, but instead we care about finite sample expressivity, because in the end, our training sets have a finite size. And finite sample expressivity, it's precisely this, the ability to fit any label set of a fixed size. So in this work, we proved two theorems. The first one, it's for quantum circuits, where we show that quantum circuits can in principle fit data independently of on the label. So let rho 1 to rho n be training set with different quantum states, and let be n capital N some poly of the number of qubits. So we have a polynomial size training set. Then for any possible combination of labels, of real labels, we can construct a quantum circuit of depth poly n such that as an observable, so M is our quantum circuit, such that the trace of any of these training samples and the observable gives the label. So this is okay, interesting, but in the end, we don't really care about quantum circuits. We care about parameterized quantum circuits, right? So we also proved this for parameterized quantum circuits, but now we had to include like some sort of distinguishability condition between the quantum states. Otherwise, this cannot be proved. And here we prove something similar, given a training set of quantum states of size n, being n some poly of the number of qubits, and fulfilling this distinguishability condition. Then we can construct a PQC of depth poly n as a parameterized observable, m of theta, such that for any possible combination of labels, we can find the parameters that classify these quantum states correctly. So this is great because the main point of these theorems was to show that our empirical findings could in principle extend to different models of arbitrary size, right? Because the experiment that we performed, we used a quantum convolutional networks up to 32 qubits, but we wanted to show that this in principle could be extended to arbitrary number of qubits and arbitrary quantum neural networks. So conclusion and
sorry, Carlos, I have a question.
Yeah.
In the previous theorem, when you are talking about these labels, I1, Y1, Yn.
Yeah.
Yes, the next one for the parameterized.
Mhm.
Yes. Are you assuming that these for any labels are corrupt are right labels characterizing the underlying probability density function, or they could be also corrupted labels or even randomized labels?
They could be anything. This is what we show here. So this is what I was talking about, finite sample expressivity. So finite sample expressivity is the ability of the PQC to fit any combination of random labels.
So here, basically, the theorem is what it's saying is that we are able to fit any distribution of labels, right? And to find a circuit that finally is going to overfit to it.
Exactly. So there exists a PQC of size poly n. This is important because, of course, if you have an exponentially sized PQC, then probably you could do more things. But PQC of depth poly n, such that for any combination of labels, then you can find some parameters that fit these labels.
I interpret this theorem about some. Please correct me if I'm wrong. That this is like eventually a trap, right, for the training, because it guarantees that we can overfit if we really try.
Yeah. I'm not saying this is useful for, like, say, in practice QML, and actually probably it's not, because this saying that PQCs can overfit. Simply it's interesting for our purpose of showing that PQCs can overfit any combination of labels and therefore can fit corrupt distributions, which will at the same time show that uniform bounds are loose. So that was the whole point of these theorems, to show that the experiments could be extended to arbitrary PQCs of arbitrary size, and therefore that uniform bounds may be loose for other setups as well.
Okay, so in some way, what this theorem is saying is to rule out the possibility of finding a case in which it is not possible to overfit.
No, I mean, there are cases where probably you won't be able to overfit. It will depend on your network. We are saying that, I think I would think it the other way around. We are saying that there might be cases that we didn't consider in our experiments, which were for this particular task, for this particular quantum neural network, the QCNN, and for this particular training set size. There may be cases outside of this where we can also memorize or fit corrupt training sets. And we show this by proving these two theorems. We can always construct PQCs of arbitrary size that can fit corrupt training sets.
Okay, thank you.
This was the main point of the theorems, to show that our experiments could be extended to other setups in principle. Okay, so conclusion and outlook. So we've seen that uniform generation bounds cannot explain the generation performance of existing QML models because of our experiments. Now, thanks of these theorems, we also saw that the results could in principle go beyond the quantum convolutional neural network. And this is a bit of shameless advertising, but along those lines, we also put a paper recently on arXiv about double descent in quantum machine learning. I'm not sure if you are aware of this double descent phenomena. Probably you are, but basically this phenomena also contradicts statistical learning theory. So statistical learning theory would tell you that as you increase the complexity of the models, then or you reduce it, you will observe this U-shaped curve, right? But what was observed very recently in deep neural network is that actually what you observe is this double descent. So as you keep increasing the complexity of the model, at some point it will decrease also the test error. And this cannot be explained by a statistical learning theory. And ChatGPT, for instance, would be here on the because these models have, yeah.
Is this linked to what people call grokking?
can you explain to me precisely what I've read about it, and I don't think it's related, but can you explain it to me, please?
What I understood is that you keep overfitting, no? You have a super overfitting model, and then you let it train, no? And the test error, well, rises, and then suddenly it goes down. It's like an emergent phenomena, and it sounds very very similar to this
Yeah.
flow. But it's not in the complexity. The axis is the like training steps.
Then might be also double descent, because I've seen many papers trying to explain double descent not only on the complexity side, but also, as you said, as like in the instead of having complexity, having training time and so on. So it might be the same thing, but only considering like training time instead of complexity and all of these things. So as I was saying, this goes in line of trying to show that statistical learning theory is not the correct theory to explain quantum machine learning. We also observed that training seems to be unaffected by this data corruption. And I like to see this paper as a call to action where, if we've seen that uniform generalization bounds are not good to explain the performance of this model, then why shouldn't we start working on non-uniform generalization bounds? And I see like trying to work on in this direction, I see like two different possible paths. The first one would be to, of course, like follow what's been done in the deep learning literature. This would mean trying to develop information theoretic generation bounds, which are known to be non-uniform and quite tight for deep neural networks. Or also try to find like good empirical generation measures by doing experiments. Say you train 1,000 quantum neural networks, see how they perform and correlate the performance with the sharpness of the local minima they end up, the training time and these kind of things, and see what kind of characteristics are aligned with generalization in PQCs. Along these lines, also, bit of shameless advertising again. This is work in progress, but it should be on archive soonish, hopefully. We take the pack Bayesian approach, which is a framework used in deep neural networks for explaining generalization. So we try to like import this knowledge into quantum models. And this is an example of a non-uniform generalization bounds. As you can see here, like it's the bound, it's much more fine-grained towards the properties of the network. These are the dimension of the Hilbert space on each layer. In the end, you have also the norm of the Krauss operators. You have a more much fine-grained explanation why quantum neural networks generalize. And then on the other hand, instead of following deep learning literature, we could also investigate like quantum complexity measure, right? So we have like a classical nail that we are trying to hit with a quantum hammer. So the question is whether we can replace this classical nail with a quantum nail. But this is, of course, easy to say, but not an easy question to answer. So I don't know. I wouldn't know how to proceed in this path. But perhaps some of you have any ideas. So this is all I had to say. Thank you very much for your attention.
Bravo.